down the periodic table, because you're adding energy levels, it gets bigger and bigger and bigger. But as you go across, because of that Coulombic attraction it was just talking about, since the nucleus is getting more and more attractive, but you're not adding an extra energy level, the atoms get smaller. So within the same row, the smaller atom will be towards the right. However, the difference between rows is more dramatic than the side to side. So something like francium is going to be, well, that's the largest, but something like, let's say mercury, is going to be larger than gallium, even though gallium is just one notch to the right, but it's several rows up. So like going down the periodic table makes more of a difference, which is also related to that Coulombic attraction thing you were just looking at. The force of Coulombic attraction is related to Z, where Z is the atomic number. The fish means proportional to or related to. So this means that as the atomic number goes up, the Coulombic attraction was increasing. But that is also proportional to 1 over the distance squared. So the further you get away, the less attraction you have. So those ones that were at further energy levels away had less Coulombic attraction. Okay, so then we're going to apply this to ions. So first of all, the size thing. Positive ions are always smaller than the atom. So like K plus is always smaller than potassium. It's lost an electron and its outermost energy level, it's definitely gotten smaller. Negative ions are the opposite. Negative ions are always larger. So those trends we just did in size, we're talking about the atom, but then if you take that atom and make it negative, now you've made it larger and larger. Or if you made it positive, now you made it smaller and smaller. Okay, so then, if we want to talk about Coulombic attraction in ion-ion attraction, we just learned that Coulombic attraction depends on the charge, the attractiveness, as well as the size. So if I was going to think about charge, I would think about the KBr versus CAS. KBr versus CAS. Now K and Ca are going to be comparable in size. They're not the exact same size, but they're comparable in size because they're next door neighbors, right? K and Ca. So I've got K here, and it's got a positive charge, and I've got Ca here, and it's got 2 positive charges, right? Because calcium has a positive 2 charge. And then bromine and sulfur, let's do chlorine so that they're neighbors again. Chlorine and sulfur are going to be neighbors. Sulfur is going to be a slightly bigger negative because of the 2 negatives, but they're going to be bigger than these guys because they're negative. But they're comparable in size. So this one is going to experience more attraction. It's going to experience more attraction. So melting calcium sulfide is going to require way more energy than melting potassium chloride, because these two are much more attracted to each other because they have double the charge, so double the attraction, and they have comparable sizes. Then if we think of two that are of similar charges but different sizes, now let's look at KBr versus NaCl. Okay, so potassium and bromine are both below sodium and chlorine, so the KBr atom is bigger than the sodium chloride atom. They have similar charges though. So the charges are similar, This one is bigger, so this one has less attraction, this one has more attraction. So it takes more energy to melt sodium chloride than potassium bromide, because these are more attracted to each other. But then what about when we're looking at both things at the same time, both size and charge? Because charge is going in integers, it's like the difference in charge between this one and this has double the charge, right? Twice as much charge. Whereas the difference in size is not double the size. I tried to picture it, so this is not twice as big as this one. And as you go down the periodic table. So it ends up being that charge matters more for attraction of ions. Charge matters more for the attraction of ions. So if I did something like took my CAS and compared it to NaCl, now CAS is definitely larger, but its charges are double that of NaCl. So this one is going to experience more attraction because of the charge beating size. And next we're going to put a series of elements in order by a series of compounds in order by most attractive to least attractive. So these are our choices: NaCl, NaF, KBr, CaO, BaO, Al2O3, and CaCl2. So when first thing we're trying to do, find out who's most attractive, the first thing you're going to want to do is assign the charges to each of these elements, because whichever ones have the biggest charges are going to be the most attractive. So sodium's in column 1 gets a +1 charge, chlorine in column 17 gets a -1 charge, sodium still +1, chlorine -1, K +1, Br -1. But then CaO is +2 and -2, BaO +2 and -2, Al +3 with -2, and then CaCl2 +2, -1. Okay, so just based on charge, who's the most attractive? Toby? Yeah, so Al2O3 is the most attractive. It has an extremely high melting point. Okay, he has no competition. Then the next one down, we have a +2, -2, but we have 2 of them. So we have to determine which one is more attractive based on size. The O's are the same size. Ca should be smaller than Ba, right? So smaller is more attractive, CaO, than BaO. Okay, then next we go to the one that's +2, -1. There's only one of those, so that's next. Then we go to these. With NaCl and NaF and KBr, they're all the same charges. Ks and Brs are definitely the biggest, they're lowest. And then these two are tied on the NAs, but the F is the smallest. So who's next? NaF. Then NaCl, and then KBr. also, if you had memorized your solubility chart, you'll notice that things tend to get more soluble as you get less attraction. Because the more they are attracted to themselves, the less likely they want to get in the water and spread out. And so these tend to be very soluble things down at this end, less soluble things down at that end. Okay.